Good morning, everyone. So today I'd like to talk to you a little bit about Tenerife and about the Canary Islands and the most important place on Tenerife, in my view at least, and that's the Teide National Park. Geologically speaking, it's in the center of the island. It's the highlight geologically of the Canary Islands. So this is what I will try to talk about in two parts. So I will try to give you a little bit of an introduction to the Canary Islands first, and then we'll discuss the evolutionary stages of Tenerife. And then there will be some highlights that I'll pick out, geological highlights, the rift zones and the landslide hypotheses, the Shield basalt complexes in the corners of Tenerife. Then we'll talk a little bit about the Las Canadas volcano, which was a large explosive episode in the history of Tenerife. And then we'll go into Teide, which is a rather young volcanic edifice, and Pico Viejo. It's only about 200,000 years that those two have been growing. And then we will also close with some views of Teide and the rifts, and we will go into some of the historical eruptions to close things off, those that have been recorded since the Spanish conquest, that is, and for which we actually have live witness accounts. So the Canary Islands, well, you all know where they are. They are off the northwestern coast of Africa in the northern central Atlantic. And they are one of several island groups. There is the Canaries here, but there's also Madeira up here, and there's the Cape Verdes down here. The Azores are up here, but they are a little different because they are connected to the mid-Atlantic ridge here, and there is no such feature in the Canary areas, although there has been some discussions about whether there's a connection with the Atlas fault system, but this has never been conclusively demonstrated. So we'll talk a little bit more about this in a short while, but here's some tourist logo that the Canary Tourist Board is pushing forward. Well, it's the volcanic experience of the Canary Islands that makes them so special. And this is exemplified with the ongoing and hopefully now ending eruption on La Palma for the last 2 days. The volcano has been very quiet, so there's hope now that the ordeal of the population is now coming to an end. And Tenerife is one of the central islands. It's been a very important place for a number of reasons. Initially, it's been important for European seafaring nations because it's actually really tall. So it's been a navigation highlight, but it's been settled by initially Portuguese, but then later Spanish settlers. And the Spanish have made it part of their empire, of their growing empire at the time. And therefore, there was a colonization effort, and Tenerife has been producing a lot of crops for a long time, which has been a very important economic aspect. And much later, at about less than 100 years ago, tourism became a major economic strand on the islands. And here's an old tourist postcard, an old postcard of Teide volcano and the Orotava Valley, where tourism has actually started back in the days of Agatha Christie and a little earlier. So I should point out that also scientifically, Tenerife has been fundamental, and there was this big discussion about how tall mountains are and what the highest place in the world would be. And this goes back to the 1770s and earlier. And here, it was ultimately left to Mr. Humboldt to confirm an earlier measurement and therefore define the height of Teide for good with 3,700 something meters. And prior to that, it was believed that if you go to the peak of Teide, you would actually burn because the sun would be so intense. And Humboldt demonstrated this is not the case if you go up there. So, and Mr. Humboldt, he visited the islands only for a week, actually, in 1799. He was traveling from Spain to the Americas, and he was very active in that 1 week. It's quite impressive. So you can trace his steps. He visited Teide volcano and the Las Canadas volcano, the Las Canadas caldera. And he also went to La Laguna, and he looked at some of the forests there in Anaga. And he, of course, spent some time in Orotava, and we'll come back later during the talk every now and then to Humboldt's observation, which have been a basis for many subsequent observations. In that time he spent there, he noted rather quickly that there is a change of vegetation if you change altitude, if you move from the coast upwards. And he also noted the sea of clouds, and here is a little depiction of this. So at a certain level, the clouds get stuck and they cannot travel further. They need to lose moisture in order to travel over the hillside. And then you have warm, dry air falling down on the other side, like a foehn effect in the Alps. And he noted that already in 1799. This realization about the vegetation changes was very fundamental, and he refined this later in Central America and in South America in particular. And he noted that it's similar to going north on the planet. If you go higher in altitude, then it gets colder and the vegetation changes as if you were to go further north. So he realized that there is a parallel between going northward and going upward. And he measures the height of Teide, as I said, and he confirms an earlier measurement. Actually, the earlier measurement was better, but prior to that, there was all sorts of random measurements, and none of them confirmed the previous one. And he was the first to say, oh, this one is pretty right. And for this, he actually got fame and glory rather than the first person who got the measurement right, which was a French person. But I forgot the name myself, I have to admit. So somewhat later, as I said, tourism became a major economic strand on the islands, and it's rather beautiful. The climate is rather beautiful, and the landscape is spectacular. The landscape is based on the geology, of course, which is our main focus. And here we have one of these spectacular geological features, the Orotava Valley. You can see the sidewall of the Orotava landslide scar. This is a giant depression, a giant landslide scar, and it's being filled in from above with new lava. So you can just about see that in that old postcard here. And of course, Teide is towering above them all. And in the right season, Teide happens to be snow-capped, but it's not all year round that it appears this way. The other major aspect here is, of course, agriculture, and this is what the Spanish colonial interests were for a long time. There was a lot of fertile land that could be exploited, and particularly in the lower parts of the island, there's a lot of plantations here in the Isla Baja, the low part on the northern side of the island. There's a lot of banana plantations, and there is also a lot of pineapple and tomato plantations. So a lot of fruit and vegetable is grown there to this day. So here's a few more impressions of the tourist kind of age taking off. This is also from Orotava. This is from the botanical gardens, reflecting this combination between beauty, vegetation, and subsequently the tourist industry. So, but let's talk a little bit more about geology now. So here is the Canary Islands, with Tenerife being one of the central islands. There's two provinces there. There is the Eastern Canaries, where the capital is Las Palmas de Gran Canaria. And then there's the Western Canaries, with Santa Cruz de Tenerife being the capital for that district. And there is, of course, a healthy rivalry between these two parts of the Canaries. And therefore, there's also two different soccer clubs, two different beers, two different, almost everything. So, and Santa Cruz de Tenerife is kind of the major place on Tenerife, although it hasn't been like that all through history. And I'll talk a little bit about this later. So Tenerife is a large island growing up from several kilometers depth. It's got a little bit of a platform surrounding it. This goes back to the late glacial maximum that this platform formed. And if you count the altitude from the seafloor to the peak of Teide, it actually turns out to be, depending on exactly how you measure it, but it turns out to be something on 7.5 kilometers in height. So this makes it the third tallest volcanic edifice in the world, and Hawaii being the very tallest with something like 8,000 meters. So the Canaries, they form a ridge on the seafloor, and there's a pronounced gravity high. Here's a little bit of geophysics, and they form a rather narrow chain of islands. And some people argue there is a bit of clustering, and indeed El Hierro and La Palma, LP and H in this diagram here, they seem to kind of grow in tandem or grow parallel at the same time. But there is, in fact, a rather convincing age progression. And this is important to note, and I'll come to this just now. So here, the big discussion that's been going on since the 70s, whether this is a continuation of a fracture zone coming from the Atlas, or whether this is, excuse me, whether this is a plume-related age progression. This has been very important in the scientific literature. And here, when we look at the oldest exposed rocks on the islands, then we find that the eastern islands, they have rocks dating back to about 20 million years, Gran Canaria about 14.5 million years. The oldest rock on Tenerife are approximately 12 million years. And then Gomera about 9, La Palma at about 1.7, and the youngest exposed of the oldest rocks in the Canaries is on El Hierro with about 1.1 million years. So looking at when the islands emerged, there is an age progression, and this would be very unlikely in a fracture-related province. In the Azores, the islands have no age progression. They're random. If we look at the Cameroon volcanic line, which is a volcanic graben, there we also have a random age distribution. Also, the earthquake intensity is fundamentally different to, for example, continental fracture zones or oceanic fracture zones, but we'll talk a little bit about this later. So this has been giving a lot of support to the plume model, but of course, there will be some fractures in the ocean crust, so they can be locally exploited. This is not to say that fractures don't play a role, but I think the Atlas fracture may not be the best explanation. So here we have a view from out on the Atlantic onto the islands. And there we have the new islands. And there is a little seamount, Las Hijas, that's been found offshore of El Hierro. And for some time, people believe this may be a new volcanic island forming. But it actually has been sampled by now with dredge cruises. And it turns out that it's actually Cretaceous in age. And it's part of a series of Cretaceous seamounts that goes perpendicular to the trend of the Canaries. So these probably have little to do with the Canaries. They're an older igneous province. So I think this implies that El Hierro is the youngest island, and El Hierro is growing and had an eruption, a submarine eruption in 2011. And La Palma is also growing, as we've seen with the current ongoing events. So the other important aspect here when it comes to distinguishing the different models of formation is the erosion patterns. Tenerife is the tallest of the Canary Islands, and it's believed to be in the height of evolution, while the eastern islands, they're heavily eroded. They're rather flat, and Fuerteventura and Lanzarote are very low in altitude. Gran Canaria is a bit more hilly, Tenerife being at its maximum extent, and the younger islands, El Hierro and La Palma, they are in their growth stage. They are mainly basaltic in nature, and they are forming in their shield stage, if you will, right now. And therefore, this would also go along with the age progression. The erosion pattern would reflect the age progression. And on the lower right-hand side, we also have some estimates about the ages of the sediments under the islands. And this is established from seismic records as well as from sedimentary xenoliths that were brought up by the lavas on these islands. And it appears that the islands on the western end of the archipelago have the youngest sediments under the islands, and that is consistent with the age progression as well. So there's a good set of geological data that would favor the plume model rather than any other model. And of course, this can be discussed, but I think the Atlas idea is less strong than the plume idea. And if we go beyond the Canaries, this is actually supported by trends we see elsewhere. For example, the Madeira archipelago has a similar kind of curvature and formation period as the Canary Islands, which actually would imply there's a larger plate motion that is at play. And if you play that game, you can come up with an Euler pole, a rotation pole. Of course, this is a theoretical one, but here the Euler pole would fall somewhere into the central North Atlantic, and you could rotate both the Madeira archipelago as well as the Canary archipelago around this Euler pole, and it would give you an age progression. If you take the seamounts into account, then there is a series of seamounts north of the Canaries that go back to 60 million years. And this would be reasonably consistent with Madeira, where we have actually some onshore examples and some offshore examples, and they would span a similar age record. So this is indirect evidence in support of a plume theory. And as I mentioned earlier, the earthquake patterns are fundamentally different. On the right-hand side, there is a close-up earthquake map of the Azores, which sit in a triple junction. And there's a lot of earthquakes and big earthquakes in the Azores, really serious ones, up to 8 on the Richter scale. And this is, of course, also the case in the Atlas Mountains, which is a tectonically very active region. But in the Canaries, the earthquakes are comparatively few and comparatively small. So there is no direct link to earthquakes in the Atlas region as well, which you can see in the lower right-hand side, while the plate boundaries in the upper diagram, or in the upper part of the lower diagram on the right-hand side, they show really strong intensities and a lot of them. So this is other evidence that is usually cited in favor of non-fracture model, of a plume model for the Canary Islands. If we look at the subterranean rocks beneath the Canary Islands, then what we find is that there's Cretaceous to Jurassic ocean crust. We know this from geophysics. And the ocean crust anomalies, they go actually across the Canaries. They're not in parallel with the Canaries. That also would imply fractures in the ocean crust are not the key issue here. There can be a discussion about Lanzarote and Fuerteventura on the right-hand side, maybe being fracture controlled, and that cannot be completely negated, I guess. But certainly Gran Canaria, Tenerife, and the other islands, they cut across these oceanic structures. And also the islands, certainly Gran Canaria is rather roundish, and the Tenerife shape is also a little unusual. If you look at fracture-related systems, like, for example, the Azores, they really align with the fractures. The islands are elongate. And this is not what we see in the Canary Islands. There we have independent fracture systems like rift zones, but they don't seem to be parallel to any oceanic structures that we know of. So there is strong evidence, in addition, from geophysics, that we have a deep-seated feeding system supplying the islands. And here is the work by Montelli et al. 2006. This is a seismic tomography, and it shows that the Cape Verde Islands, the Canary Islands, and the Azores are all supplied by a deep mantle anomaly, and it can be traced down to the core mantle boundary. So the Azores are a somewhat special case, because it then appears that they are a plume that intersects with a triple junction, a plate boundary triple junction, while the Cape Verdes and the Canaries happen to be plumes that are intraplate in the classic sense. So here's a little more of this work by Montelli et al. So there is these anomalies underlying the Cape Verdes and the Canaries, and they're rather distinct. I mean, it's very hard to argue that they are not there. So they, in my view at least, seal the discussion that fractures near the surface would be the controlling factor. I don't think that works. I think the Atlas fracture would not strictly be able to cause mantle anomalies at 2,900 kilometers depth. So I think the plume model is the stronger one for now. So that brings me to this summary here. This is a diagram from my colleague, Juan Carlos Caracero, from the Canary Islands and Tenerife. And Here is his view of bringing this together. We have a mantle plume that rises up, and here we have activity in the western part of the archipelago. And for whatever reason, there's two active islands right now, and their history seems to alternate. And there can also be some activity on some of the central and eastern islands, but this is mainly due to drag, as people argue. This is a drag of plume material because of the plate motion. And the highest number of eruptions, historical eruptions, happened on La Palma, with half of the historical eruptions occurring there, and all the other islands have more sporadic eruptions at this stage. So this allows me to focus in and zoom in on Tenerife a little more. Tenerife is the largest island in the Canary Islands, and it also has the highest elevation. It's, according to the people on Tenerife, it's the jewel in the crown in the Canary Islands. It's also got a very large population, approaching almost 1 million by now. And the population density is very high. You may be aware that Sweden has a population density of about 25 people per square kilometer. So there's a lot of people in the Canaries. And I've just been on La Palma, just coming back a few days ago. It's quite a shock when you kind of come from this densely populated archipelago back to Sweden, or the other way around. So this gives you a flavor. And there is, of course, a high number of visitors every year. And I'll mention this in more detail later, but Teide National Park has more than 4 million visitors every year. Actually, that's more visitors than Yellowstone National Park. So there's a lot of tourists, but 12 million a year pre-corona. And this on top of the population there, it's really a popular place, let's put it like that. So here's a few impressions of Tenerife from our recent overview article, which I sent to Ulf to distribute. And this is some of the highlights there. There is the old shields in the top left. This is the Los Gigantes cliffs. There's big basalt stacks. Then we have the Las Canadas volcano, a little younger, with these large ignimbrites. This is the Grandilla ignimbrite. And then we have the Las Canadas caldera forming at the peak of the evolution of the Las Canadas volcano. And there is debate about whether this is a vertical collapse caldera or a lateral collapse. And in my view, it's a bit of both, actually. I think they don't exclude each other. And after the Las Canadas volcano terminated and collapsed effectively, we have Teide growing, and then later Pico Viejo. This is a funny coincidence. Pico Viejo means the old peak, but actually it's the younger peak, which geology has shown now. It's a parasite cone on the flank of Teide rather than an older volcano that's being swallowed up by Teide. But the early geologists had some issues distinguishing this, and this is how the naming got a little bit, the wrong way around. The current activity on Tenerife is following mainly along the northwest rift zone, and this is what I'm showing here. And you can see from the northwest rift zone, you can see the other islands, making it very clear that you're in a chain, in a volcanic island chain. And the recent eruptive record is given on the right-hand side. This is based on carbon dating mainly and historical observations. There was an eruption in 1492, which Columbus described while he was passing the island. He saw that there was an eruption on the hillside, and this has now been identified. The vents have been found. The Boca Cangrejo eruption. Then there was 1705, the Guima eruption. The Garachico eruption in 1706. Then there was a bit of a break, the Johora eruption 1798, and then the youngest of the eruptions on Tenerife is the Chinero eruption of 1909, and we had no eruption since. So, I mean, given the rhythm, it's a little irregular, so it may well take another 100 years before another eruption on Tenerife occurs, but I think there's a high likelihood that another eruption on Tenerife will occur. So the fundamental structural architecture of Tenerife is defined by 3 major rift arms, giving it this characteristic shape. And the recent eruption, the historical eruption, they all occurred along these rift zones. The 1706 and the 1704-5 eruption are certainly on the rift zones, and the 1909 is a little bit more central, as is the 1798 one. But that is effectively where the rift zones meet the central complex, and therefore the rift activity is the main risk that we're seeing right now on Tenerife. Teide volcano erupted the last time in the Middle Ages. There's the Lavas Negras eruption. It's dated to about 900 AD or maybe a little younger, but it has not erupted in the historical record. And chance is it will not erupt in the next little while. I think the probability of a rift zone eruption is a lot higher. It's kind of similar to the La Palma situation. It's a long ridge-like volcanic system that has sinter cones growing, and they may produce lavas that go all the way to the sea. So this is what we would have to expect for Tenerife as well, if an eruption would occur. So this is the Lavas Negras. I mentioned them. The cone on top of Tenerife, the dark cone here, it's also part of the Lavas Negras eruption. Prior to that, the volcano had a wider crater and was a little lower in altitude. And the Lavas Negras, they have traveled down the Teide edifice, but they didn't reach the sea. They're also phonolithic in composition. They're a bit more viscous than the usual rift zone eruptions. The southern rift is a little bit of a peculiar feature, and very often in structural geology, people argue that when you have a triple-armed rift systems, you have two strong arms, two active rift arms, and one passive rift arm, one that just responds. And if you want to use that concept, then the southern rift zone in Tenerife would be the passive arm. There is some sinter cone alignments, but there's no historical eruptions, and it's the weakest of those arms. So there is some lovely kind of alignment of cones, but they're all a little older. And at the southern end, the cone alignment reaches the sea, and you get some shallow lava sea, lava ocean interaction. And there is some pillow type structures, which I'm showing here in the lower right hand side. There's also some phreatomagmatic cones, which is the image in the top right hand side. There's some nice phreatomagmatic layers here at Montaña Amarilla. And this is the weaker rift arm to my understanding. The stronger rift arm is the northeast and also the northwest rift arms. Here is an image of the northeast rift arm, the Cumbre Dorsal, as it's known in the local terminology. And here you see the Sea of Clouds. It's at an altitude of about 1,000 meters. So the island continues under the clouds. But this is viewed from Teide summit, and you see this is a long ridge extending towards this old shield, Anaga, it's called, the old shield in the distance, which is actually in this image under the clouds. So here's a Google Earth image of the same thing. We see the ridge-like structure, and you can almost see a green belt in that image. And this is actually the Corona Forestal, the crown of forest, which is mainly fed from the Sea of Clouds. It's actually not a lot of rainfall, but there's a lot of clouds and precipitation, dew effectively from those clouds, and that feeds these pine forests. And therefore, we have a ring of this forest. So if you go up to the volcanic center of the island, you have to go through this crown, this forest crown. And it's a rather lovely kind of thing. It's very cool. People love to go there in summer. The local people go there for picnics into the forest. And this is a very important biodiversity reservoir of the island, actually. So now looking at the north eastern rift zone in a little bit more detail. Here we have a bit of erosion that allows us to look into the lower parts of such a rift zone. And the important thing there is we have dikes in there, a lot of dikes. So if you look here at the hillside, there's a dike, 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 there's a dike. And if you look at this road cut here, there's a large dike parallel to the rift. And this is what makes up the rift zones. A lot of dikes and sinter cones, volcanic vents at the surface. So here, if you look at road cuts, and I had a PhD student looking at them in a little bit more detail a few years ago. Here's the student Audrey, and she was driving along the road of the rift zone multiple times a day, I guess, and she mapped all these dikes, and we got permission to drill the dikes. We did magnetics on them, and we were also able to date some of them. But the effective knowledge here is that there is a lot of dikes that feed these rift zones, and that's what the rift zones look like underneath. And we were also allowed to go into gallerias, water tunnels at the time. It's no longer allowed these days because there was a bad accident a few years ago. But when you go into the rift zone in one of these water tunnels, you see that the dike density increases the further in you go. And at some point, the dike density is really, really high. More than 50% of the rock mass is dikes inside these rift zones. So here's one of these gallerias, and there is about 1,000 of these water tunnels that were dug because there is a real water shortage on the islands because of the large population density and the tourism industry. And we, as I said, had permission at the time for various trips into some of them, but this bad accident in 2007 prevented us from doing any more work in them. But here's a few impressions from back in the day. So these are there to harvest old water that's stored inside the mountainside. And there's a lot of dikes. And Frances Stegen, who is still here in Uppsala, she did part of her PhD on these dikes. And she published a lovely paper in 2012 on the chemistry of these rocks. So here is a TAS diagram, a total alkali versus silica diagram of these rocks from the northeast rift zone, including those we were retrieving from these gallerias, these water tunnels. So here's a little more of an impression, but I don't think we need to go into detail. But these are lovely basaltic rocks. They're mildly alkaline, and they have a lot of pyroxene, olivine, and when they're a little bit more evolved, they have plagioclase as well. And they form nice fractional crystallization trends, but there's a whiff of assimilation as well that we can see in some of them. And it seems that the central rift zone system is compatible with the central volcanic system, with the Teide, nowadays Teide system. Back then, there was no Teide. Back in the old days when this rift zone formed, there was mainly the Las Cañadas system. But isotopically speaking, many of these rift zone rocks, they would likely be fed from the central volcanic system. So this brings me on to looking from the rift zone here, which is the cluster of sintercones in the foreground, towards the Teide volcanic system. And you can actually see the lavas negras here on Teide. You see these dark lavas coming down, and the cone. This was the last eruption of the Teide system. You also see Montaña Blanca here, which is a phonolite complex at the periphery of Teide, and we'll talk a little bit more about this later. Many of the felsic rocks seem to come out in the periphery of Teide. Here's another block of phonolite that came out in the periphery. And this here is the beginning of the northeast rift zone, stretching all the way to Anaga Shield. And here, another image of the same thing, just a little clearer maybe. This is the lavas negras that came down. This is the Montaña Blanca system. And here we have the sintercones of the northeast rift zones. And a little further, the erosion sets in, and there we can see all of these dikes. So let's talk for a little while about the connection between, the central system and these rift zones. Well, Teide sits for a good reason at the major central point of these three rift zones. This is where magma ascent is probably easiest. And there's also this large collapse area, the Las Cañadas caldera. Some workers want to argue it's three nested collapse calderas with vertical collapse, but then there is also the argument that this is a giant lateral collapse. And intriguingly, if you date the rocks here that's in between these collapse basins, they date at about 0.5 to 0.6 million years, while those associated with the lateral collapse, they date at about 200,000 years. So I actually think what we're seeing is that there has been vertical collapse followed by lateral collapse. So this central edifice has been going strong for several million years, and at some point it overgrew to a point where lateral collapses occurred, which are depicted here. We have several along the rift zone. Here is another one, for example, and eventually this central part collapsed as well. And after that, Teide volcano started to grow, and then Pico Viejo grew at the side of Teide volcano. So that's the rough geological history from our current understanding. If we look at the rock distribution, we have the central stratovolcano, and this is a Spanish slide again from my colleague Juan Carlos. And we have the central Teide volcano, which is mainly phonolithic in composition, and we have the rift zones. And the southern rift zone is a little older. It doesn't have any very recent eruptions. Only the northeastern and northwestern rift zones have historical eruptions, and they are mainly basaltic. So we have this intriguing system of basalt on the rift zones and phonolites, more evolved rocks, in the central system. Let's talk a little bit about rift zones now. They are kind of peculiar in my view. We have rift zones only actually forming at big volcanoes. Small volcanoes don't really have rift zones. And while people initially thought it's the plume pushing upwards that makes these triple armed rift zones, I'm starting to diverge from this a little bit. My personal take is that experiments are not strictly supporting this. If you have any area that's pushing upwards, you actually get a radial pattern, not a triple armed system. And since triple armed rift zones only occur on larger volcanoes, it seems that they're actually a feature that develop due to instabilities on the volcano, rather than being something that the volcano inherits to start with. So here's a few images that we published a few years ago in our Teide book for Springer. And here we see that once the volcano has grown to a certain size, instabilities can develop. And then we get these large landslides that are well documented for many parts of the Canary Islands. And then we get nested volcanism. And Teide is one of those nested volcanoes inside one of these major landslide scars. If you look at the systems in more detail, you will find that the old shield volcanoes, Taino and Anaga, they have their own triple armed rift systems. They are independent from the overall structure of the Tenerife rift system. And if you look at Hawaii, for example, there's also these triple armed systems. And in fact, the triple arm systems in the Canaries are actually better developed than those on Hawaii. If you look at recent vent distribution, which is the diagram on the right-hand side. So there, the red colors mean high vent density, the yellow colors mean somewhat lesser density, and the gray colors mean low density. Then you see that the vents are really clustering around those rift zones. And looking at the map of Tenerife and looking at El Hierro and La Palma orientations, it's very hard to come up with oceanic structures or so that are in a singular orientation. They're much more randomly distributed. And therefore, I'm starting to feel increasingly that this has to do with how edifices grow and collapse, how we make these rift zones rather than being inherited fractures from somewhere else. So here's another view of the Cumbre Dorsal, the northeast rift zone, but this time viewed from Anaga, from the old Shield Massif. And you see it's a long ridge, and it extends from the central system all the way to the old Shield. And if we look at Anaga, the old Shield, which is a little older than much of the other parts of the island, there we have to assume that several independent shields formed and eventually they coalesced to make the current island of Tenerife. And here we had a shield volcano that's older than 5 million years, no active volcanism there, and it's deeply eroded, quite mountainous actually. And it also had evidence for larger landslides. Once this Anaga edifice had grown to a certain size, there was a large landslide to the north, which I'm showing here in this diagram. So this is a landslide scar. And I was mapping dikes many years ago together with a colleague just at the end of my PhD. And what we found is that there's dikes that are oriented this way and other dikes that are oriented this way. And there's younger dikes that wrap around the collapse scar. This led us to conclude that there was a development from the island itself that has caused the rift orientations. And there's also a submarine deposit or a landslide deposit that can be linked to these events. So in very brief terms, this is the dating we did, and this was the dike orientations we did. Anaga started off as a ridge-like system, very much like the rift zones we see today, very much like La Palma, southern Cumbre Vieja volcano. And eventually there was an instability growing at the northern side of this ridge. The dikes responded to this instability. The intruding dikes could feel the change in the stress field. They were curving around. And only after that, a passive third arm formed. That's the one to the south. And this gave rise to a triaxial rift system. But it's not something that was always there. It actually started to develop with instability of the volcano. So this led us to come up with this little model that we had a shield system that eventually got unstable at some point and therefore developed a triple arm system. And we actually can see that in the dikes. Some of the older dikes are sheared. There was a creep element. And then the newer dikes, they wrap around the landslide scar and they cut the sheared dikes. So we have a good geological control on this. And my colleague, Tom Walter, who is now at GFZ in Potsdam, he did a numerical model in order to test this. He introduced a fracture system into the theoretical construct of Anaga, and he allowed the interior of this fracture system here to slide outwards. And what he was realizing is that you get a compressive regime here, but an extensional regime on the opposite end. And this is what the passive rift system actually is. It's just a passive extension from instability on the other side. At least that's what we concluded in a study that we published a few years ago. And we then did some jelly experiments. And this was actually quite intriguing because we wanted to see how it's possible to make triaxial rifts in gelatin volcanoes. And we did hundreds of these jelly volcanoes, and we failed to make triaxial rifts. Only when we introduced an unstable sector, and that was just, we had no kind of friction, and we put washing up liquid in the unstable sector. It was really slidey, if you will, and we injected ink at that point into the area between the unstable sector and the rest of this gelatin edifice. Then we started to make triple armed rift systems. So this is the result, really. In a stable situation, we get radial dikes. If we have injection in the stable part of a little jelly volcano that has a sliding part, we still get radial dikes. If we inject into the unstable part, we also get radial dikes. But we can actually make triple armed systems by injecting into the transition zone between the unstable and the stable part. And therefore, I am pretty convinced that these triple armed systems in the Canaries, they link to growth of volcanoes and instabilities that result from rapid growth of some of these edifices. So this is something we had already mentioned. Tenerife has these three arms, these three rift zones. And that brings me on to giant landslides. But looking at my watch, I think we just filled the hour. So I would say we'll have a short 5-minute break just to stretch our legs. And I'll fill up my coffee. And then we can continue talking about giant landslides and Tenerife. Into it, and the next topic I'd like to focus on a little bit more is the giant landslides. They have caused a lot of concern, of course, during the recent eruption on La Palma. People were really worried that some giant landslide might come out of it. I've tried to calm people down by saying there has been a lot of historical eruptions on La Palma without a giant landslide. But of course, they are geologic reality. So these giant landslides did occur. They are enormous collapses. and they are really thousands of cubic kilometers, and they have long run-out distances for hundreds of kilometers on the ocean floor. They occur in particular on steep intraplate volcanic ocean islands. So Hawaii has them, Canaries, Cape Verde, Reunion, etc. So they have a long kind of distance to travel. They fall down a lot. They are tall islands, so they fall down and they travel accordingly. So gravity is particularly favorable for these landslides on these intraplate ocean islands. However, they're very rare on human timescales, but they are not infrequent on geological timescales. And here in the Canaries, we see that there is some old landslides on Lanzarote recorded, on Fuerteventura, Gran Canaria, several ones, and there are several on Tenerife to the north as well as to the southeast. And then El Hierro has them, and La Palma has them as well. So let's look at them in a little bit more detail. So here we have one of these giant landslides, the Guima landslide, and you can see the landslide scar here, and it comes around here. And actually there was one of the historical eruptions on the rift zone, which is the northeast rift zone here. There's Teide again, and this is the Orotava volcano from 1705. And it happens to shed lavas, or has shed lavas, into the Guima landslide scar. The Guima scar is several 100,000 years old, and it's partly been filled with debris, but it's got a very marked wall here. And on the other side, here's the wall of the Orotava slide. So there has been landslides coming from both sides. And here we have the Misheke slide, the Orotava slide, the Guima slide I've just shown, and also the Icod slide, which happened a little younger. And this was the slide that gave rise to the depression in which the Teide volcano has been growing. So these slides are rather large, and they seem to shed from the flanks of these rift zones, and usually they're enclosed in between the rift arms, therefore emphasizing this triple-armed rift shape that we often see. So this is a view onto the Orotava landslide depression. Here's the Orotava landslide. You can really see the low ground with Teide towering over it. And here we have the northeast rift zone behind it. Actually, this is an intriguing phenomena, because the Orotava landslide depression is one of the main agricultural hubs on the island, and it's one of the most densely populated areas. It's a bit wind sheltered. It has a lot of rainfall because of this particular situation. So in a way, the geology is favoring agriculture in that area, and Humboldt was very impressed with it. And he said he could settle there. He liked it so much. And he described 3 sinter cones inside the Orotava Valley. But unfortunately, there's only 1.5 left, because people have quarried them. And they use the little volcanic particles for supplementing the soil for agriculture. And here we see 2 of them. This one is half gone. This one is still there, but the third one is completely gone. So this is an interaction of humans with the geology, and it led to this really densely populated, very fertile area that we're still exploiting today, we as in society as a whole. So there's Humboldt's Mirador, the viewpoint where Humboldt apparently made his observations, and there is a bronze statue of Humboldt sitting there and making notes. And this is a big thing for the island, of course. So, but talking about these landslides in a little more detail, there was this model some 15 years ago, and this led to a lot of, I guess, bad press is the word. There was this model that the La Palma island could collapse, and it could send out these pressure waves, cause a major tsunami, and the tsunami would be strong enough to reach the Americas, and it could actually wreak devastation and havoc in the eastern coast of the US, for example, New York, Florida, and these areas. Now, big debate, but of course, it's not impossible that such a landslide occurs. It's actually quite feasible, but whether it would take exactly this shape and have these consequences, that's of course a matter of debate. So it will certainly cause a splash But will it go all the way to the Americas and destroy the seaboard, the eastern seaboard of the US? Well, that can be discussed, of course. Chances these landslides may slide very slowly. They may not fall. There may not be a splash in the classic sense. They may go in portions rather than in one go. So we have actually too little information about this. So then I'd like to talk a little bit on the three old shields, the former areas that have grown independently. And there's the Anaga and the Taino Shield, and there's Roque del Conde. Roque del Conde is the oldest exposed rocks on the island, which is likely part of a central shield. Chemically, this area here seems to be isotopically similar to some of the rocks here. So maybe this was a larger area here. But we have the independent Anaga edifice, which I mentioned earlier, and the independent Taino edifice, and they are also isotopically a little different. So they were likely independent islands, and eventually the whole system grew into one larger edifice. So this is the model from the evolution of Tenerife. We likely had these three main shields, the Anaga and the Taino shields, and what's increasingly called the central shield. And the central shield then grew into the Las Cañadas volcano later on, and that overgrew the entire system, and therefore covering the lower areas of these marginal shield volcanoes, and therefore bringing them together. The Anaga volcano occurred in a period about 5 to 4 million years. The Taino volcano is yet older. It has rocks up to 6 million years. And the central shield has the oldest rocks with almost 11.8 million years. And the Las Cañadas volcano is a lot younger. And this is topping all of these other systems there. So just a few words about the Taino Shield. It's a rather spectacular little edifice, and you can already see on the DEM, the erosion patterns are very different in these areas in the old shields. They're less smooth, they have more erosion that caused them to change their topography and their landscape. And here we have also several old landslides. The Taino Shield had several landslides going to the north, like the Anaga Shield actually, and therefore it's pretty clear it was its own edifice with its own structural evolution that later was made part of the larger island of Tenerife. If you go to Taino, this is how it looks. It's actually a spectacular landscape. I understand that one of the Planet of the Apes movies was filmed there because of its spectacular landscape. And it's got a sequence of basals and breccias, and it's got also collapsed breccias. So it's a spectacular place to look at how ocean islands develop. And I'm happy to talk a little bit more about this later, but I will just give you a little summary here. There's a debris avalanche deposit in the center of this image, which marks the collapse area. And then there's a collapse space in infill again. That's the rocks to the right here. And then there's the older shield material that's to the left. And that's the red marked rocks here. So you can actually, when looking around and walking around there, come up with rather intriguing or rather interesting development history that can then be transposed to many of the younger phenomena in the islands as a whole. So this is work by a former PhD student, Marc-Antoine Longpré, and he came up with this little diagram. He came up with a stratigraphy with an age progression, and he finds these steeply dipping old shield rocks. Then he finds the first debris avalanche, and then he finds that there's some ultramafic rocks first, and then later trachytic rocks, and then a second collapse, a second debris avalanche. And after that, we have the sequence starting again with ultramafic rocks, more basaltic rocks, and eventually some more felsic trachytic rocks. So this is also what the central shield would have experienced, Teide being the phonolithic trachytic final product after a major collapse that occurred about 200,000 years ago for central Tenerife. So here's a few impressions of how these collapsed rocks look like. These are large-scale debris avalanche deposits, so breccias effectively, and they're quite thick. So this is what we believe to be the result of a major collapse area. And Marc-Antoine, the student, he was from North America. He was French Canadian, and he loved Mount St. Helens, so he always compared it to Mount St. Helens and the collapse of a flank of a volcano. And then he also found that there were some explosive deposits amongst the breccias. So he argued that there was a big explosion associated with this collapse, like we have seen at Mount St. Helens. And I think the analogy is quite reasonable, although the scales are very different, of course. So then we have these ultramafic rocks that follow after the landslide. And this is very typical that many of the giant landslides, they bring these very crystal rich rocks in the Canaries. And here we have some Anomalies. That's a very pyroxene rich lava. And some of the inclusions are rather large. Some of the pyroxenes are quite massive. And this is probably a function of decompression. If we move part of the edifice, we decompress the magma storage system underneath, and then the magma might rise up. We see this on Iceland as well, that decompression due to melting of the glacial ice has led to a burst of volcanism. So this is likely a similar phenomenon, although we have no glaciers in the Canaries, but the landslides may decompress the plumbing systems. So, and here just a little impression, and oops, it brings up these really amazing rocks, and these are now from El Hierro, where we have the youngest landslide, the El Golfo landslide, and this is the rocks that came up after the landslide. And this is also good for the industry in the Canaries, because the olivine crystals there and the peridotite nodules, they are harvested for making jewelry, and this is what you can buy there. And they are rather lovely, very high quality, in fact. So this is something that has been given a boost to the island's industry over the last few decades. So I'd like to talk a little bit about the last Canadas volcano, now the central edifice that then emerged after the initial shield basalt series on the corners of the island. And we know the Las Cañadas caldera, this part here in the center of the island, but there's a lot of older explosive rocks associated with the Las Cañadas caldera and volcano. And here's some impressions from southern Tenerife, from Pandas del Sur, the southern strips, that's the translation. And there we have these rather thick ignimbrite stacks and quite a series of them. So there must have been some gigantic explosive eruptions of phonolytic chemistry happening at that point. And there we see channels filling with some of this erosive, some of this material filling these erosive channels. So here we have one band, and it thickens a little bit here in the channel. And this is typical for ignimbrite deposits. They even out topography because they come like a blanket, if you will. And here's two of my mapping students a few years ago looking at the Abrigo ignimbrite. And it's a rather gorgeous rock, actually, beautiful and light in color. But when the sun is shining, it's almost too intense because the crystals reflect the light. And then it's actually very hard to see things at some point. So here's a few more impressions of various rocks. Here's the Pumice Ridge Grandia ignimbrite in the south of the island. Sometimes we have a bit of water involved. Here's some accretionary lapilli that occur in some of these ignimbrites. So there may have been some interaction with seawater or with local ponds that were affected by these large eruptions. And here is one of these lapilli deposits. They're mined for agriculture. This is from one of the quarries. And they give rise to very good soil because they make the soil very fluffy and they store water. The vesicles in the pumice are very good for that. And this is something the local economy has been profiting from for a long time. So then the erosion can can sculpture some of these bizarre landscapes. Here, if you have some of these inclusions, like the ones here and here, and the weathering affects them slightly differently because these basalt inclusions, these picked up inclusions may not weather in the same way. You get these rather weird landscapes that are then called landscapes of the moon or things like that. But they're very popular with tourists, of course, but these are erosive landscapes rather than anything else. So the Las Cañadas caldera here, the caldera wall, it's a phenomenal geological repository. We can see a lot of the record of the volcano there, and you can actually drive along the whole margin here of the caldera, with Teide being here. And there's different hiking trails along the Las Cañadas caldera wall, and you can find most of the big ignimbrite deposits that we see in the Pandas del Sur also in the caldera wall. And the caldera wall is now partly being drowned, being filled up by intracaldera deposits. You see the flat area here, that's intracaldera material. And here you see the partly eroded caldera wall. That gives you an insight into the Las Cañadas caldera. So there is also a few of these phonolite domes associated with the Las Cañadas caldera, and they weather out and they make what the locals call sombreros. This is these large rock hats standing out, and they can be also outside the caldera, and you'll surely see some when you go to Tenerife. And what's also intriguing is in the marginal areas of the Las Cañadas caldera, where the erosion has weathered back some of the caldera wall, you can see a lot of intrusions, minor intrusions, mainly plugs and sheets. And there you actually have some cone sheet-like intrusions. These are intrusions that are inward dipping towards a central part of the former reservoir system, one believes. And these are spectacularly exposed there. This is inside the caldera at a place called Bocatauce. And at the same place, you can see some concentric intrusions. So there has been work postulating that we had concentric as well as radial systems. And some of these concentric ones are cone sheet-like, others are more ring dike-like in their geometry, and that would imply pulsing of the system. You get cone sheets when the system moves upwards, when it's under pressure, and ring dikes when the system deflates, potentially having caldera collapse style. So what you also see quite frequently is these type of features, these flowers of rock or roses of rock, as they are often referred to in the Canaries. And these are effectively former lava tunnel fills. So if you have a lava tunnel and there's lava going through the tunnel again, then it will harden, and the columns, the solidification cracks, they will form perpendicular to the cooling surface. They make these rose structures. The lava tunnel might erode away, but the fill might remain, and then you get features like this where you can actually see a former lava tunnel fill. Here's one of the plugs in the old pre-caldera rocks, and this is called the Cathedral. It's one of the major plugs that is still sticking out. It's only partly covered by the intracaldera fill, and it's got also these horizontal lying columns, so implying that cooling was from the side walls inwards rather than the other way. While up here you see that the columns swing around a little, so actually you can argue that this may have been the shape of the intrusion. There was a country rock surrounding it, but the country rock is gone. And also the part that would have been above these rocks here, or the continuation of these rocks here from the caldera wall, is gone. And this allows us to reconstruct the Las Cañadas volcano from taking these former intrusions and taking the rocks in the caldera wall. And the Las Cañadas volcano would have looked a bit like this, probably as tall as Teide, but it would have filled up the entire area of the caldera that we see today. Would have been a massive edifice. And we see many of these barrancos, these valleys, being truncated. That's a good sign that there was a big volcano with a big relief, and it had a lot of topography that eventually then disappeared by vertical and lateral collapse. So then we want to focus a little bit on Teide National Park. And I mentioned it earlier, it's one of the most popular parks, not just in Europe, it's actually one of the most popular parks worldwide. And it has a huge number of visitors. More than 4 million people go there. That's pre-corona numbers. It's been obviously going down a little bit due to corona. But the beauty about it is you can travel around freely, and it's not a restricted park. So you can actually bring a car. You're not allowed to drive off-road, of course, but you can walk from most areas. And it's been established in the 1950s, and it's been going strong ever since. It's part of a UNESCO World Heritage Site, and I've been part of the UNESCO assessment at the time. And it's a spectacular geological as well as a biodiversity enclave, and therefore it's quite worthwhile protecting in my view. So here's some impressions of that. It's the caldera and it's the rift zones that attach to the caldera, but it's of course also the central volcano Teide with the lavas negras and its cone here. You might find that the cable car is operational when you go there. It's recently reopened and it allows you to go up there to about 3,500 meters. And now they're building a restaurant up there, so you can actually have a meal up there if you like. And it starts at about 2,000 meters. But one of the problems is that most people stay near the coast. So if you drive up in the morning to 2,000 meters altitude, and then you get elevated with a cable car to 3,500, and then you walk up the last few hundred meters, a lot of people get really unwell up there. So be a little bit careful, be mindful of that if you have a chance to go. So we talked about this earlier. There is this connection between the rift zones, the landslides, and these edifices growing inside. And this is just to remind you that this is likely what applies to Teide as well, and the Las Cañadas caldera. So here we have an aerial view. It's a NASA image, and you see the Las Cañadas chopped off volcano. It broke off here, and you have this new volcano growing inside. And here's Pico Viejo sitting on the flank of this new volcano. And likely Teide grew too tall, so we have actually a lot of eruptions coming out at the sides now. And here is Rajada and Montaña Blanca, and they form their own little lava flows. So a lot of the activity has been in the periphery of Teide over the last little while. So it's believed that Teide might have reached its maximum elevation possible, and magma is actually trying to go to the sides instead of traveling all the way up. So here's a few impressions now, and here you see some of these peripheral faunalite areas and some of the lavas that came off it. This is the lavas negras, the last eruption from the summit. And here we have some of the older rocks of the Las Cañadas caldera. And of course, here we have them also in the wall to the Las Cañadas caldera. So here again, we see the peripheral faunalite domes and their lavas. This is the central Teide edifice, and here's the Las Cañadas caldera wall. So just a few nice impressions to ease you in and make you excited about going to Tenerife. Hopefully it will work as a trip in January for you. And this is what I mentioned earlier, the 3 caldera model, that there may have been 3 vertical calderas, seeing them here, 1, 2, 3, but there is, of course, the lateral collapse evidence, and there's an offshore debris avalanche out here. So certainly it did collapse laterally, but it may well have collapsed vertically as well during the time of the big Las Cañadas ignimbrite eruptions that we have recorded in the Pandas del Sur. This, in fact, is a remnant that stands inside the caldera. It's called the Tree of Rocks, and it turns out to be the most photographed geological feature on the island. Everybody who has a chance goes there and takes a picture, and it sits right in this area here in between 2 of these supposed vertical collapse calderas. So it's a remnant of the former stratigraphy, and this is the other part of the remnant. So here we have one caldera basin more bordering another caldera basin, and actually the infill is very different here because of this different boundary here. So here we have a thicker infill, and here we have a thinner one. There is some hydrothermal alteration along these older rocks, and we dated the hydrothermal alteration. It predates the lateral collapse. It's about 0.6 million years old. You can do clay dating there, and it's beautiful. It's beautiful colors, but it's certainly part of the Las Canadas volcano and not of the younger Teide system. So here's one of my former students, Graham Nickel, posing at the beautiful site of the Los Azulejos. Azulejos means tiles, the colorful tiles. The Spanish tiles gave name to this. And indeed, the rocks here have been quarried in the past for making colors and for making paints. So they're still used in certain ceremonial festivals on the island to paint the streets, for example. So these are greens and pinks and all sorts of rather beautiful colors, depending on oxidation stage and what fluids have been interacting with them. And you can see them here interacting with the younger lava. So here you see these upstanding older hydrothermal rocks and younger lavas starting to bury them gradually. The tree of rock, I mentioned it earlier. It's, of course, a temporary feature. It cannot last forever. It will fall one day, and maybe in one stormy night will take it down. But why does it actually exist is a question I get very often. And it's because there's two dikes that have gone through there. There's two hard igneous rocks amongst the sedimentary package. The sediments of the caldera infill, they erode very easily, but the dikes up here, this one and this one, they are harder to erode, and they allow this part here to be more massive, while the lower sedimentary part is eroding back very rapidly. And this can, of course, not last forever, unfortunately. So, as I said, this is the most photographed feature on Tenerife, and I think there's estimates that there must be something like 50 million pictures of this by now worldwide. So the national park, it's clearly the centerpiece of the island, and here we have a beautiful view of it. It's the hosting Teide, which is the tallest mountain in Spain, and it's here shown above the Sea of Clouds with the lavas negras. This is just a few beautiful images for you. And here we have another view of it with Montaña Blanca in the front of it. So this is Montaña Blanca Pumice. Now, data is, of course, used for the local brand of beer. I mentioned it at the very beginning. There's a brewery on Gran Canaria, and there's one on Tenerife, and they are in heavy competition. And Dorada is the beer from Tenerife, and Tropical is the one from Gran Canaria. So this one hosts Teide in the logo. And I should warn you, do not ever possibly order a Tropical on Tenerife. It will be frowned upon. So you can only order Tropical in the Eastern Canaries, and there you will be praised for that choice. But on Tenerife, I think Dorada has to be your choice. So, but let's go back to geology, just a little bit of joking aside. I mentioned there's a cable car, and we have been contracted by the cable car company to write some tourist books now on the geology, because they need to spend a certain proportion of their income on outreach. And so we've been lucky enough to secure some support from them. And now they have enough money actually to build a restaurant up there. This is the cable car station there. And now they're building a new edifice there for making it a fancy Michelin star type restaurant that's going to be up there. So you can dine up there and enjoy the views. And a few words about Teide's summit. This is the current summit. It was quarried in the Spanish Civil War for sulfur, so it's not a pristine feature. The sulfur was used for gunpowder, obviously, and it's a bit of a dump right now. It's effectively a mine site or a quarry site. So you still see the sulfur in there, and this is looking into the quarry. It's filled up effectively. There's no crater as such. It's just a hole full of rubble, of material left behind from the sulfur quarrying. And there's a bit of fumarole activity on certain days, but it's very weak. And it's good enough to do some gas chemistry. There was a paper just recently by a US group. They looked at helium isotopes and things like that, and carbon isotopes in these gases. So, but it's usually quite weak. You need a special permit to go up there. You can go up to the cable car station for free, but for going the rest, they only allow a small number of people up in order to not deteriorate the site any further. But here's some of the fumaroles, and here's some of the sulfur crystals that form around these fumaroles. It's lovely, but of course, as I said, it's not a pristine natural site. You can see that it's been quarried before. So here, the final shape of Teide, this final cone up here, is part of the Lavas Negras eruptions, and there must have been a bigger crater prior to the Lavas Negras. So when you look at the shape of Teide, this was likely the pre-Lavas Negras edifice with a larger crater that we have to assume was there, and this cone eventually grew inside this. So the medieval cone here, again, this is one of my Spanish borrowed slides. The medieval cone is a very young feature, and the old crater is probably, or has been, a lot larger. So let's talk a little bit about Teide and the active rifts. And most of the active volcanism and the recent volcanism is happening in the central edifice and on the rifts. We mentioned that earlier. And here we have another beautiful kind of photograph with the phonolithic rocks here coming off the main cone, but also in the periphery. So the Lavas Negras and their extent is approximately this, including the central cone, and they're dated at 1150 before present. So here's some features, beautiful levees of the Lavas Negras, and the cable car station is just up here. And then you have these gorgeous lava flows that can still be seen, of course. And this is one of the central parts of the national park. There's a lot of obsidian in them, so they were chilled rather swiftly, and gorgeous things. But unfortunately, without a permit, you're not allowed to take any souvenirs. But a lot of people do nevertheless. But if the ranger catches you, they will be very unpleasant with you, and they will record your name and send you a very unpleasant letter. So, but otherwise, they cannot really fine you. So a lot of people are not taking the rangers overly seriously and are actually taking souvenirs, despite the fact that we're not supposed to. So another intriguing feature of this area is Teide's eggs. And these are actually accretionary balls that have come from the lava flows and rolled off the lava flows, because these lava flows happen to work on steep grounds and steep slopes. And we've been seeing them form on La Palma actually just a few weeks ago. And here we know that these are little snowballs, if you will, that detach and they roll down on the active lava flow, and they accumulate the sticky parts of the lava flow. And here you can actually see the accretionary layers of them, and they will then roll down slope even beyond the tongue of the lava flow, and then they make these eggs. In Iceland, they would be called troll footballs or soccer balls of the trolls, but here they're called Teide's eggs. So the Pico Viejo cone, as I said, it's actually a little younger, and it's a parasite cone. It happened to form on the sidewall. And here is a view into the Pico Viejo crater. And this is also marked by the somewhat different rock chemistry. So it's got its own little supply system, it seems, and it's not directly connected to the central supply system of Teide. Here you can see the cone sitting on the side of it. And here it produced these very plagioclase rich lavas. This is a 20,000-year-old lava, a Pa'ai lava, and it's super plagioclase rich, all these dark kind of crystals here. That's a lot of plage that we see in them. This is one of the rock roses, which also came from this area. And this is again a filled in lava tube. It's just at the fringe of the national park. and it's one of the main sites. You will surely see it when you go to Tenerife. And well, we discussed the formation of that earlier, but this is likely also connected to that system. Quick note about lava tunnels. Lava tunnels can form if we have encrusting of a lava flow, and then you might insulate the interior. And some of these lava tunnels have been very useful for local people, because in the old days there were a lot of pirate attacks and people were sheltering inside these lava tunnels. You also have different species that live in these lava tunnels exclusively. There's different species of spiders that lost their pigment and they live in complete darkness in these lava tunnels. So it's actually not it's not so nice, because once you put the lights on in these lava tunnels, you see there's a lot of dark spiders in there. I didn't enjoy that. So, but neither did my wife, which is depicted in the upper right. That was only a small lava tunnel we explored at that point. So, but here's one of the bigger ones, the Cueva de los Vientos, the Cave of the Winds. And this is a spectacular one. You can go in there as well. And it's protected, of course, but you get hard hats and lights and things like that, and you can look at them. And yeah, here's the spiders. So there's these regular spiders that you have outside on Tenerife, but then when the spiders moved into the lava tunnels, they lost their pigment. They decided that they don't need that anymore because it's dark for most of the time. And then it's the same type of spider, but black. And there's a lot of them in these lava tunnels. So what you also get is these lava stalactites. Sometimes the roofs are melting in these lava tunnels, and then you get dripping lava from the roofs, and they make these beautiful features. Another feature you find associated with these lava tunnels, and often at the surface above the lava tunnels, is these hornitos. It's a Mexican term. It's basically a rootless cone. It's when lava was flowing underneath, but you had a skylight, you had an opening, and then things were pouring out there, and they make these little mounds at the surface. And in fact, the local people use the hornitos to map the lava tunnels. Often you have drained lava systems underneath these hornitos, and you can actually work them out. So here is one hornito, here's another. So there must be a feeder system connecting them underneath. So lava types, there's loads of lava types, of course, and we have Pahoy Hoy lava. This upper one to the right is from Pico Viejo, and then we have these lava channels. So you'll get to see a lot of spectacular features there. Here's more of these lava channels on the Teide itself, and it forms these main flow channels and the levees. And this is what we also see right now on La Palma, for instance. So here's a few overgrown examples, a few older ones, but you can still recognize the lava features rather well. I mentioned earlier that we have these phonolite plugs at the side and phonolite vents at the side of Teide, and there is a little map showing them. So much of the phonolite activity over the recent geological history has been clustering around the volcano. And the simple argument is that this is because magma isn't stupid, in inverted commas. Why travel all the way to the summit if you can take a shortcut to the surface? So this is likely what's happening there, that it's just energetically more favorable for the magma to come up at the sides. And this gives rise to these large phonolite complexes in the periphery around the base of Teide volcano. And here is several of them, the Jara Dome and the Montaña Blanca pumice deposit. So, and this gives rise to these beautifully light-colored rocks inside the caldera. And this is a bit like a lunar landscape. It's rather fascinating to be there. And this is another main feature for the outstanding natural beauty that was used to justify the UNESCO's status of the national park. And these phonolite domes and complexes, they gave rise to a number of big lava flows. And here's some impressions of them. And again, they can be seen inside the national park, as well as further down near the coast, and some of them even reach the sea. So here's one of these spectacular lava flows, and because lava is not like water, it doesn't run all the way down the hill, it can actually freeze on a hillside. We have one of these lavas that were actually freezing while traveling down a hillside, and this is also something you can see inside the national park. So I think we've looked at that, so I'll skip on, and just a few words about the rifts again. We have in red here the phonolithic central part, and in green here the basaltic rocks of the rift zones. And this can be mapped in terms of vents, and this distinction is very clear. There is a clear difference between the central complex and the rift zones, and we can look at the chemistry of that. And I had a PhD student, Sebastian Wiesmeyer, who was looking at this in more detail. So I'll run you through some results very briefly at least. And here we see that the central volcano produces these phonolites, and the rift zones, the basalts, and in the transition zone here, we actually have some magma mixing. So there we have these spectacularly mixed deposits. And here, for example, we see different eruptive regimes being superimposed on each other. We have phonolites and we have basalts, and we have this in alternating sequence. And this is a beautiful outcrop. It's called la tarta, the cake, because it's made like cake layers. So the chemistry of these is, according to Sebastian Wiesmeyer's work, is giving us this trend of basaltic rocks, that they go into these mixed transitional rocks, and then we have the evolved phonolites. But intriguingly already here, the evolved phonolites, they don't follow a traditional fractional crystallization trend. They actually have a trend that's across the traditional trend, and this led Sebastian to postulate that many of these phonolites are products of recycling of some sort, while the basaltic rocks, they form by fractionation of some sort. So let's see. Here we go. So Bowen would imply that we have a lot of basalt if we don't want to do fractional crystallization, and we produce a lot of more evolved rocks. In Bowen's series, it would be rhyolite. Here, of course, we don't have a lot of rhyolite. We have phonolite and trachyte. And if we look at the eruptive volume, then we find that actually these phonolites, they are quite voluminous compared to the basaltic eruptions. So something is at odds with the traditional scheme. We have a lot more of these evolved eruptions and a lot higher volume than what would be expected from fractional crystallization. So there we have been formulating this idea that we might be recycling a lot of fractionated rocks, maybe from the Las Cañadas volcano, and this could give rise to these higher volumes we see in the central system of Tenerife. So Sebastian was then looking at all sorts of parameters and trace elements and also isotopes, but I'll be rather fast with this, but he came up with these diagrams here, and he can work out that the fractional crystallization part of the evolution is controlled by feldspar removal, while the higher ratios, particularly when it comes to isotopes for strontium, can only be explained by some sort of recycling of hydrothermally altered material that must have been involved from older parts of the island edifice. So here's the various isotope plots, and it seems to be not sediments. Sediments would be plotting out here, but it seems to be mainly the DHF rocks, the Diego Hernandez Formation, which is part of the older Las Cañadas volcano that give rise to these red rocks, the felsic rocks in the center of the island. So, and here's a lead isotope diagram, and the Atlantic sediments are plotting out here. So they are not the ones responsible here. And if we look at the old shield volcano like Anaga, it's that red pink field here. So that doesn't seem to be the case either. The Roque del Conde shield, the central shield, that's a bit more similar isotopically. So there seems to be a connection. And here, when we look at some post-collapse lavas, they overlap in part. And when we go towards younger and younger lavas, then we can see that there's an overlap with the central shield. So this led to the conclusion that it's not the old shield volcanoes, it's not the sediments, but it is recycling within this large, ginormous edifice that has developed that might give rise to these larger volumes of material that erupt in the central volcanic system on Tenerife. So partial melting of older igneous country rock was the conclusion. And of course, it's up for debate, like everything in science can be argued backwards and forwards. But this was the conclusion we put forward. And other groups, John Wolfe, for example, they have come up with similar ideas now that crustal melting may be a major phenomena. And we tested this with these numerical models, the energy constrained AFC models. And it would actually work according to these models, and some of the phonolites would have potentially a high proportion of recycled ignimbritic phonolite material from earlier in the history of Tenerife. So when it comes to the mixing, these central systems, the Teide phonolite system here may be, of course, thermally supplied by a basaltic system underneath, and it gives rise to these phonolites in the central part. The basals of the rift zones would be what we have to assume to be the parental rocks. And when we just happen to have basaltic material rising up and hitting part of this phonolithic reservoir in the center of the island, we get these mixed rocks like the Montaña Reventada eruption, which is at the margin of the national park. And here we are going to talk a little bit about the historical eruption. The Reventada eruption is actually plotting in this area. It's falling in this area. So, and this is mainly young volcanic eruptions. So for the last few minutes before I close the lecture, I'm going to talk about the historical eruptions now. They are the ones that have been witnessed, and historical in the Canaries means since the Spanish conquest, because we have no written records prior to that. So this is the historical eruptions, and the oldest one is the 1704, 1705 eruption, and it actually erupted from several vents. We have Siete Fuentes here, we have Fasnia here, and we have Arrafo here. So it's a rift eruption, and it follows the rift trend, but it had multiple vents. They were not active at the same time. They were erupting sequentially with a small overlap. So the eruption progressed at the time, and it was mainly an unpopulated area. So it wasn't a huge problem for the population. But putting it onto a map, here we have Siete Fuentes, we have Fasnia, and then Arrafo is in the upper part of the Guima Valley, and it sent lavas down, but the lavas didn't reach the coast. But they're lovely kind of analogies to the current eruption on La Palma. This is pretty much what we see there. We have a sinter cone type eruption on the ridge, and it sends lavas down towards the coast, and with enough eruptive volume, it would reach the coast, of course. So then we kind of can look at the Arrafo volcano here. It's nested inside the Guima landslide scar. So here's the Arrafo volcano, here's the Guima landslide scar. So this would be this place up here. And then we can look at some of the other vents. This is the vents here inside the national park. This is the little piles of sinter material that have been forming, but only very short lava flows that have been emanating from this part of the eruption. And here you can actually see them, the Fasnia vents. And this is now something you can actually walk to inside the national park, and you can visit that and look at it in quite some detail. The 1706 eruption, this was probably the economically most devastating eruption on the island because it destroyed the harbor of Garachico. Garachico was the main port for the Americas at the time. This is Garachico, and this was a nice harbor basin. But the lavas coming down from the rift zone, it's this eruption here, 1706, they were partly filling in the harbor basin here, and this made the port rather narrow. And here's an old drawing, an oil painting, and it shows how the port was partly filled, and it forced the local economy to rethink, and then the port was moved to Las Americas, near Los Cristianos, and eventually to Santa Cruz, because it's also more wind sheltered. So the evolution of Garachico was really strongly altered. It never really recovered from this, and it's now a lovely little town to visit, but it has no economic relevance as such any longer. So this is a few impressions from there. Here's the port, here's the port down here, and you see the lavas that have filled in the port. And this makes it very awkward to maneuver larger ships in that area. And it ended effectively the history of Garachico as a major port city. So the 1909 eruption, it was, of course, already happening then when photography was a possibility. So there is actually some photographic evidence. And strangely enough, it led to some volcano tourism already back then. So here you have these images of local people with their mules bringing up tourists, and they were watching the volcano. And here you have a postcard from 1909, somebody saying, oh, looking at the beautiful eruption at Chinchero. And it's along this rift zone that it happened, again, in an unpopulated area. So no harm was done as far as I am aware of. So there is this older eruption. This has nowadays been added to the historical eruptions because there's a logbook entry of Columbus. He describes an eruption in the Sierra of Tenerife, i.e. on the ridge of Tenerife, not on the peak of Tenerife. And this is the Boca Cangrejo eruption, this one here. And this can therefore be dated at 1492, and it has been confirmed now with a carbon date that this must be the vent and this must be the eruption. So here we have the Boca Cangrejo eruption and the vents, and they are now part of the historical eruptions as an witness account does exist. So the 1705 eruption, that's actually on the flank of Pico Viejo. This is this one here, the Chahora eruption, but it didn't leave the main caldera. It was confined within the caldera basin. And again, there were several vents. There was a little crack opening in 1705, and this produced nice lavas, very beautiful, but also in an area that was entirely unpopulated. So again, no harm was done. So this is a view of this, distant view and aerial view. And here we have a good record of how these eruptions occur. Very similar again to the La Palma eruption, only that the La Palma eruption is a bit bigger and it affects a populated area. That's the big problem there. But the model of the eruption, the type of eruption, is well understood from older eruptions in the Canary Islands. So this is just a view into one of the vents of the 1705 eruption. Of course, there's a lot of debris in there now, but this was one of the gas vents. And this is the possibilities of hiking in the area. You can look at these recent eruptions, and there's a whole series of hikes. We're currently working on a book to guide people to look at these historical eruptions. And this is some of the maps we're producing where you see the lava fields and the eruptive vents of many of these historical eruptions in the rift zone. And the beauty about Tenerife's National Park is everything is accessible. You can walk there freely on various hiking trails. So this is really bringing me to the end. So I'll wrap up now. As I said, the national park is the highlight of Tenerife geologically, and it's breaking records. At least prior to Corona, it was breaking records with more and more visitors being recorded, more than any other national parks in Spain. And it even surpassed Yellowstone National Park by now in terms of visitor numbers. And if you're interested, there's a few things. I think I previously made the Teide volcano book available to Ulf. If you don't have it anymore, Ulf, you can let me know. I can send you a PDF of the entire book. The Geology of the Canary Islands, I don't have that as a full PDF, but yeah, you can buy this with Elsevier, I'm afraid, but it's not cheap. But most of the important aspect for Tenerife are in the Teide book, so I can make that available again if you need it. And here I'd like to kind of say thank you. And yeah, Merry Christmas, in case, you know, the holidays will be coming very soon. So I thought in case I missed my chance to wish that, I'll do it now.